And this gives you the mode of f with frequency p. But it's telling you that mode so it's really giving you the frequency decomposition of f. It's telling you that for p positive this is 0. So that's telling you that there's no negative frequency modes, because if you have so you apply this, so this tells you this means the lemma means that the Fourier transform of f only has positive frequency modes. With respect to u. If it had one negative frequency, you would do suppose it had so you express f as a Fourier integral over its Fourier modes, and suppose that you have so this is just delta proportional to delta p plus omega. Okay? So so for p, so if you consider p positive, this is true for p positive. If omega is positive, then if omega is positive, then this will be the argument of delta will always be positive, and so that would be 0. But if omega is negative, it can be 0. Sorry, it can be, the argument can be 0 if omega is negative. So if you express f as a Fourier integral over Fourier modes, and there are any modes that have an omega negative, that have negative frequency, then the argument of the delta would be 0 for some p positive, and so this could not be 0. So the fact that this integral is 0 for all p positive tells you that f only has positive frequency modes. And now you can apply this here. Okay, Q is the equivalent of this. Well, I'm looking at this here, so this is the same as this, obviously, with Q being this. Q is this, and well, that's it. So this tells you, from the lemma tells you, that phi lambda only has positive frequency mode with respect to capital U.
Mark,
Yeah?
do you remember the sketch and proof? The idea?
I have it here somewhere. see it here somewhere. Have a look at it and see if you understand it or not. It's not a trivial proof, so that's why I'm just using it, but it's all detailed there. So. Okay, so this means that phi lambda up only has positive frequency modes, only has positive frequencies with respect to capital U on and you do the same thing for the up R modes. Okay, so the up R modes phi lambda up R so that's all we've done is swap. We've swapped right and left. Okay? Swapping right and left means complex conjugating and changing the sign of capital U and capital V. So you go here, you complex conjugate it and change the sign of capital U. So that's this here. Sorry, I included this. The theta is obviously not, well.
Theta is included.
Yeah, it is. It's not included in the swapping of. I didn't want to include it because it's not included in the swapping of. In changing the sign of the capital U in front of it. So the theta here. Oh, sorry. Well, it does. It does. So theta. We're looking at the left modes. So yeah. So obviously these are the only have support for theta. For U positive. Because these are the left modes. These ones will have, so these ones will be exponential of minus pi omega kappa. Now you change complex conjugated, change the sign of U. And these guys are right modes, so they only have support for U negative. And the N's and the Y's and the R, which carry no role in this.
When you say H minus, and then you press this line up to H plus L,
yeah, well, that's why I've changed it to capital V positive.
This is yet to V goes to 0.
Sorry?
This is yet to after V goes to 0. This. So.
What do we see it, right? Oh.
So.
Okay, I think I know what you mean. The L star modes. The L. The L star modes. No, sorry, what do you mean? I'm looking at the L star modes. So the R, these modes, I'm looking at their value here.
Yes.
And for the other modes, I'm looking at the value here.
Yes. So the U that you set on H minus, but it seems to be H minus HR minus and union HL plus.
Yeah. Well, that's why I'm saying, why can't I say V equals to 0?
Oh.
That's why you change it to V equals to 0. So along here, and for all real capital U. Okay. So now we've built modes which are positive frequency with respect to capital U. Okay. And these expressions readily give us the Bogoliubov transformations. So we can combine now. Now, I'm still using the little p modes, and instead of the up modes, the little up modes, I'm using the capital up modes. Little up modes were positive frequency with respect to t, capital up modes are positive frequency with respect to capital U. The up bar modes play the role of the left region, and the complex conjugates, and this for all of them. Form a complete set in this. So we can expand phi in terms of these modes. So now, just distinguish between, make sure you can tell when I write little up, capital up, when I write K versus kappa, and so on. Okay, and now we can define a vacuum, or a quantum state, which is annihilated by these annihilation operators. So the Unruh state U is defined via as a state which is annihilated by these guys in left and right, up, capital up, and capital up bar. So what is the equivalent of this vacuum state in flat spacetime? What's the equivalent of this in flat spacetime? How many states do we know in flat spacetime? Okay. So we don't have a huge amount of options left. The linear one we've already seen what the equivalent is. Okay.
This should be Minkowski, but it is Minkowski. But
Why is it Minkowski and why but? Why yes and why no?
If it is Minkowski, then U, big U, is a proper time of a free-falling observer.
Where?
Either in 1 or 3.
So it is a tricky question that I've asked, and yes, but it is Minkowski, but is probably the best answer because it is Minkowski, but we're almost there. So these guys, this state is defined using modes, which are positive frequency. These ones are positive frequency with respect to t. And these are positive frequency with respect to u on h minus. So this would be the proper time of an accelerated observer. So that's why it can't be Minkowski. Minkowski vacuum state was defined with respect to as using modes which are positive with respect to t. All modes were positive with respect to t, And so, and T is the proper time of an inertial observer in flat space-time, which is a freely falling observer, whereas this mode still includes modes. This vacuum state is still defined using modes, which are positive frequency in respect to a time which is not the proper time of inertial observer, so it can't be Minkowski. But we have Minkowski sized it to a certain point, because now before we are using T instead of these guys, now these are with respect to capital U, which are, capital U is a fine parameter along H minus, so it's an affine parameter along a null geodesic that's crossing H plus, if you wish. Remember, we use a slightly loose notation when we say an observer infalling. It's not an observer really, it's a null geodesic, so it cannot be a massive observer, but it's importantly it's the affine parameter along a null geodesic that's crossing through. So, so this is the affine parameter along H minus. So we have, so along a null geodesic, it's an affine parameter along null geodesic. Before we had little ups, which were positive frequencies with respect to T, which was not defined parameter along any geodesic. Now it is a null, it is along a geodesic. So that makes us get closer to Minkowski. This means that it's not quite Minkowski. There is no, I'm not aware of an equivalent of this state in flat space times. It was a catch to the question. But now we're going to this, whatever we did with the up modes here, we're going to do it for the in modes as well. We're going to do the same thing for the in modes, and then we will get something which is the equivalent of Minkowski. So finally, define, so I have a capital in and in bar, capital in bar, the same factor element. So just the same way as these modes were positive frequency with respect to capital U, these ones are positive frequency with respect to capital V on H plus. They're positive frequency with respect to capital V on H plus. So now we can use capital in bar, capital up bar, and the complex conjugates. So they form a complete orthonormal set. You can expand the field in terms of these modes. And define the state as the state which is annihilated by these annihilation operators, and that's the so-called cardinal Hawking state. So what's the equivalent of these modes? What's the equivalent flat space time of this vacuum state? In custody. Because, well, there's different ways to look at this. One of them is it's defined using modes which are positive frequency with respect to affine parameters along geodesics, null geodesics. That's one way of looking at this. Another one is this is defined as modes which are positive frequency with respect to a time, capital U, with respect to two times, capital U and capital V, which are well defined everywhere in the full maximum extension of the space-time. And capital U and capital V give you, as they go through the reals, they cover the full maximum extension of the space-time. In here, we had little t. The little t blows up at the horizon. You need patches. T is equal to plus infinity here, and t is equal to minus infinity here. So we were using modes which were positive frequency with respect to a coordinate, time coordinate, which was irregular somewhere inside the spacetime, the full maximum analytic extension of the spacetime. When you go back to flat spacetime, to the Unruh effect, we had the Wiener modes, and the Minkowski modes. So the Minkowski modes were positively with respect to t, but t was regular in the full maximum analytic extension of the spacetime, as opposed to in Schwarzschild spacetime. The Wiener modes were positively with respect to eta, and eta was just a fine parameter for an accelerated observer. And that blew up at those horizons. Okay? So in here, where we're using modes which are positive frequency reflected at time, which was not well defined in the full maximum linear extension of the spacetime. This is the equivalent of the little t here, t in Schwarzschild, which is not regular everywhere in the full maximum linear extension of the spacetime. This is the equivalent of capital U and capital V, which is a regular coordinates in the full maximum linear extension of the spacetime. A consequence of this, and something I haven't touched upon, I've tiptoed my way over this, is what every time I say 1 and 3, I don't talk about 2 and 4. Okay? The reason is this guy, this time coordinate t is just not well defined, it's irregular on the, it's infinite on the H plus and H minus. And in fact, because of this, the corresponding vacuum state, the Wiener vacuum state blows up here. So by that I mean, if you calculate the R set, the expectation value, the renormalized expectation value of the stress energy tensor when the field is in the Wiener vacuum state, in the case of flat spacetime, and you do it in coordinates which are regular here, so not in Wiener coordinates, in t coordinates, but the vacuum state is the Wiener vacuum state. But you calculate t mu in the Wiener vacuum state, renormalize, this is after renormalizing it. This has nothing to do with ultraviolet divergences. This has to do with the definition of the vacuum state, which is a global constant. When you calculate the renormalized expectation value of the stress energy tensor in the Wiener vacuum state in coordinates which are regular on the horizons, so tt, that blows up. This blows up in as you approach, I don't know what we call them, I'll say H, the cosmological horizons, the accelerated, these horizons in the Wiener horizons in flat spacetime. Similarly, if you calculate the expectation value of the stress energy tensor renormalized in the, say, Bowler, which is defined using T for all modes, for the in and out modes, that if you do it in coordinates which are well behaved on the future and the past horizon, so this is not a coordinate issue, this is a vacuum issue, that blows up as you approach the future and the past horizon. On the other hand, if you calculate the renormalized expectation value of the stress energy tensor when the field is in the Minkowski vacuum state and you're in flat space-time, you do it in coordinates which are regular on the Wiener horizons, that is regular on the Wiener horizons. In fact, this is just 0. Okay, renormalized expectation value of the Minkowski vacuum state is just equal to 0. Similarly, if you calculate the renormalized expectation value of the stress energy tensor when the field is in the Hartle-Hawking state and you approach the horizons, because it is defined using modes which are positive frequency with respect to time coordinates which are regular in the future and the past horizon, this is regular. Okay? Now, next lecture, on Wednesday, I'll show you what the values are, and they correspond to this, and they have some physical features. So we've got the lecture on Wednesday. Then next week is the last week. Wednesday next week is the final exam. So we didn't determine if next Monday we do a lecture or not, because there's an exam on Wednesday. Maybe we should not do a lecture on Monday, right? It seems like a very short amount of time to do, less than 48 hours to do material. So let's do the last lecture on Wednesday. I'll just finish giving the physical features of these states, and then maybe I'll touch upon Kerr. I'll say a few words about Kerr. There's Kerr, things that we could do is Kerr, laws of black hole mechanics, thermodynamics, and particle detectors. Particle detectors will probably need a lot of more time than just 2 hours. So maybe I'll just touch upon CAR. I'll see. But anyway, we'll do that, we'll finish, and then exam next week. Okay. Thank you. So Wednesday there's a lecture, even though the place is closed, but I'll give your names to the reception, and I'll leave you to the sign-in to get a bank holiday. That's the rule.